I'm Cindy Kelly, Atomic Heritage Foundation. It is Wednesday, April 25th, 2018. I am in Oak Ridge, Tennessee, and I have with me Justin Baba. And my first question for Justin is to please state your full name and spell it.
Justin Shekwaga Baba, and that is Justin. Shekwaga is Shekwoga, and Baba is Baba.
Thank you, Justin. My first question is to tell us something about yourself. Where were you born, and why? How did you get interested in becoming a scientist?
So I have an interesting story. I actually was born in Jos, that is Jos, in Nigeria, and born in 1971, October 26. And I grew up in Nigeria, and I had the opportunity to go to American schools, and eventually I ended up in the U.S. in 1990 to go to college. But my desire to become a scientist actually began in middle school, as I discovered that I was intrigued by the history of what others had accomplished and discovered. And also I realized I also was intrigued by the human body. But I knew at that point that I did not want to be a medical doctor, but I thought it'd be kind of fun to do medical related research that could have an impact on the lives of many people for many generations to come. So that was kind of the motivation for me to get into science.
So were your parents involved in science?
No, they weren't. But my parents did understand the value of an education, and they really inculcated that in me and in my siblings, and they encouraged it. And I remember my dad, always used to say, "Son, whatever it is that you think you want to do, dream big. Who knows? It could happen." So yeah, it's been an interesting journey, but they have been very supportive the whole way.
So did they follow you to the United States, or are they still in Nigeria?
They're still in Nigeria. They've had a chance to come visit. Unfortunately, my dad has not been able to come on site, but they have followed my career, and are really curious about what I do. And because my background in graduate school was in biosensing, and in looking at coming up with diagnostic tools for various diseases like diabetes. So I've actually got to work with my dad, who's a type 2 diabetic, over the past 20 or 30 years, as he has, kind of lived with that condition. But that became a focus area of mine in graduate school.
Was it coincidental that you were working on type 2 diabetes, or did you know your dad had it?
It was absolutely not coincidental. So my dad's older brother in the late 80s was diagnosed with diabetes, and when he was diagnosed, he ended up having his big toe amputated, and that's how he found out he had diabetes. He didn't know he had a wound that hadn't healed, and it turns out that his story is not unfamiliar here in the U.S. Diabetes is the primary cause of amputations in the U.S. other than blunt trauma. And so once he had his big toe amputated, my dad heard about it and went and got checked that day and discovered he also was a type 2 diabetic in the late 80s. And so since then, my dad has been, trying to live, with diabetes. So that was a huge motivation for me. It was, okay, what can we do to help diabetics? And my uncle, by the way, did not do a good job managing his diabetes, and he died within a few years. So that kind of has been a driving motivation for me to see what can be done to help diabetics better manage the disease and be more compliant and have a good and fruitful life. And so far, my dad's had lived with it for over 30 years, so he's doing well.
Well, that's wonderful.
Yep.
That's certainly a great story. So tell us about your scientific career. What have you been working on?
Oh man, I've gotten to do some really fun stuff. So when I was in graduate school at Texas A&M, the Department of Energy, who has a long history in medical developments and advanced instrumentation for medicine, for everything from for cancer treatments to medical imaging, which is now ubiquitous, for PET, SPECT, CT technology, even MRI. They at the time were looking to make an impact in other areas that were not easily addressable by NIH. And one of the areas that they identified was the issue of organ transplants, and so there was a group here at Oak Ridge that had proposed to work on a monitoring technology for liver transplants, and the sensors group here at Oak Ridge has a long history in developing miniaturized sensing and telemetry systems, and so they were a good fit. But what they lacked though was the biophotonics. And so when they originally put in the proposal, the reviewers came back and said, you guys need a biophotonics expert, somebody that actually does, biosensing, And so they were led to my professor at Texas A&M, Dr. Jerry Cote. And that's kind of how we connected. And so, we got involved with that project. And I remember that our first studies we did up at University of Louisville, because the MD on the project, he had an appointment at the VA hospital there in Louisville. And also, he was a neurophysiologist PhD. And I remember we did early studies looking at putting this probe to monitor perfusion. And so the big issue is with liver transplants, within the first couple weeks is the critical period. After the first couple weeks, if there are no complications, typically the patient probably will do okay. But within the first couple weeks, the biggest issue is clots, and so clots lead to lack of perfusion. So being able to monitor that in real time, which they're unable to do, because the process now is they just take blood draws and send it off to lab for chemistry, and that can take hours before they get a result back. But if you can have a sensor that is on the liver that in real time, right after the transplant, can provide the medical staff real-time information on the perfusion, on the health of the liver, then if something starts to go awry, they can catch it early, possibly do interventions via drugs, or in certain cases the person needs another transplant. So that was the goal. So I got involved in that project and got to meet some ORNL investigators. Nance Erickson who was one of them, and we hit it off. So we had a great time. We had fun. We did a lot of work, and then in the ensuing years, we kept running into each other at conferences and the IEEE Engineering Medicine Biology Society conferences, and I remember he asked me, he said, "So when you're done with your PhD, what are you going to do?" I said, "Well, I'm going to go into academic research, right? And he said, "Well, have you considered the national labs?" I said, "What's that?" So he starts telling me about Oak Ridge National Laboratory and the fact that this is the largest science lab, Office of Science lab. They do open science. Pretty much, if you come up with the idea, if you can propose it, if it's illegal, you can get it funded, they'll let you do it. Now granted, Department of Energy had a pretty broad mission, and you need to be within their mission space. So needless to say that they recruited me out of graduate school to come and actually do biomedical, develop biomedical sensing technologies. And so since then, I got to work on a project that was called Awake Imaging. And the Awake Imaging project, the goal was to image the brain and to do functional imaging in the brain, which means to look at brain function, to help be able to pick up stuff like Parkinson's, Alzheimer's, and also neuroblastomas, which are really hard to diagnose, but to be able to do it non-invasively. And so there was a team of us, included Oak Ridge National Laboratory, Thomas Jefferson National Accelerator Laboratory, and Johns Hopkins University. And we actually developed a scanner that can image, and we did the difficult thing. We did it in animals, in mice. So we could image and track a mouse without any anesthesia, without any restraints, moving around, and could image the brain and could literally pick up, brain function. And so that was a neat project, and I got to work on that for several years here. So that's one of the funnest projects that I've gotten to do here.
That is phenomenal. And that was transferable to humans?
Yes, we actually did a clinical pilot at Johns Hopkins where we imaged. We got to image 4 out of 5 patients that had neuroblastomas, and they're come for their follow-up PET scans, and we were able to track, do motion-corrected imaging of their brain.
So this imaging you developed, what's it called today?
Well, it's still called awake imaging, and there are a few companies that are looking to commercialize this technology. It is not in the clinic yet. I wish it were. Actually, was at a hospital recently, and I had to have a CT scan for a cardiac procedure. And I was asking the technologist, I said, hey, do you guys have access to motion corrected imaging? He said, no. He said, I wish we did though. And I asked him why. He said, well, just the other week, a little baby had come in, and they had done a CT scan of the baby. They were trying to image the baby. He said it was a nightmare. So that technology really needs to make it to the clinic. It will have a tremendous impact on brain diseases and related pathologies.
And the reason it's not brought further along now is that, as you're explaining, something to do with DOE's mission statement was kind of curtailed?
Yeah, so the Department of Energy has since lost its medical mission, which kind of has been interesting for me because, for the first few years, it was fun. It was wide open. We got to do some really fun stuff. But due to, certain things that have come up, the Department of Energy has focused really more on its core mission, which is, energy efficiency, renewable energy, and those directions. At Oak Ridge National Laboratory, however, they still have an isotope development program. And the purpose of that, and a lot of people are not even aware of this, is that the medical isotopes that are utilized for procedures today, the base material comes from the national labs. They're developed at Oak Ridge, and then the commercial vendors get those base materials and they spin it in the cyclotrons and come up with all sort of radiopharmaceutical drugs that are utilized for everything from imaging to chemotherapy treatments.
I don't think many people know that. It all comes from, is it mostly Oak Ridge is the producer of these isotopes?
Oak Ridge is a primary, producer of these isotopes.
Well, that's great. So you were telling us that DOE is now focused on energy issues more. So how does that translate to your work?
So for me, I got to do some interesting work to transition from imaging and tracking motion in mammalian biology to looking at plants. And so one of the things, the areas that in terms of energy has been renewable energy sources. So there's a lot of unknowns about how long the fossil fuel resources are going to last, but and so there's been a big push worldwide to look at can we utilize renewables a lot more and make that a bigger part of our mix. And so part of that stream was that we're going to take switchgrass. During the Bush administration, they really pushed for switchgrass to be converted, take switchgrass and convert that to bioethanol, which then ethanol can be used as a fuel for cars. And likewise, the Oak Ridge National Laboratory led a consortium that sequenced the genome for the poplar plant, for populus. that's a tree that grows, and it grows pretty fast. And so within 7 or 8 years, you can grow it as a crop and harvest it. And the nice thing about it has a lot of mass. And but the conversion of that biomass to bioethanol is a lot more difficult because it's tied up. The cellulose is easy to ferment, but the lignin, which gives the plant cells their rigidity, that is very difficult to degrade. So there's been a lot of work looking at that, and some work based off of the genetic information they had, that they've been making genetic variants to see if they can come up with a variant that can withstand the elements. In other words, grow outside in everyday weather, and grow fast and develop a lot of mass, but also be easier to decompose into bioethanol. And so one of the things that we were doing, we took the technology that we had developed to image, everything from blood flow in mammalians to brain activity, to seeing if we could image the upflow of nutrients and material within the plant itself as these plants are growing. So that was an interesting twist.
That's fantastic.
Yeah.
Yeah. So what will that tell you as you understand better this upflow?
Well, so that provides information on in terms of nutrients and how quickly those nutrients get taken up by the plant and also converted into biomass. So it can give quantitative information in terms of if you're trying to separate out different variants or phenotypes that you have, which might be the most feasible options or for what you're trying to accomplish. So for optimization. Then there's also the other issue of characterization, of actually characterizing the actual mass itself, the cellular structure that the plant is actually developing and producing. And so being able to look at that with medical, with medical imaging now, we're applying that, as applied to plants, and looking at the plant cell itself, and looking at the molecular signature of the plant cells, which can provide good quantitative information that can then be correlated to how much yield they get in terms of bioethanol from that plant mass.
So are there commercial entities knocking on your door saying, when are you going to get these poplar trees ready for me?
Well, that's a good question. Probably the person to ask about that is Jerry Tuscan. So he'll be a good one. But yeah, I know that work is ongoing, and they do have some collaborations with industry folks. I think one of the top plant genome companies, I think they're based out of North Carolina, is working with them. I know some of the variants that I actually imaged came from that company. But yeah, so there's that that part of it aspect that is right in DOE's mission, because renewable energy is a big part of DOE's mission.
Well, it's fascinating. This is wonderful. So I guess you should. We could look to the future, and we won't need fossil fuels anymore.
Well, we'll see.
We'll see.
We'll see.
That's great.
Yep.
So Justin, is there anything else you want to add about your life as a scientist, or the future of science research, or any?
Well, I'll say this much, that it's been very rewarding, and it continues to be really rewarding. And the neat thing about the National Lab is, it was true what they told me way back then, which was, if you can conceive of it, if you can get somebody to fund your idea, I mean, you can do it. You have the opportunity to really try different things. Now, granted, we are mission focused, but still within that mission, there's broad opportunity, and I'm sure you'll hear from others too that talk about working on stuff that applies to clinical, and stuff that applies to clinical that can then be translated and applied directly to DOE's core mission. So there's the things that go from clinical to plants, like in imaging, and then there are things that go the other way, that where technologies are developed in DOE's core mission that then can be translated to other areas. such as, I know advanced manufacturing is a big area. And so like part of this biomass thing is, when you extract the ethanol out of this biomass, you have leftover, material. And what do you do with it? Well, you can convert that into carbon. And then you can form carbon fibers, and then from those carbon fibers you can build stuff. And so there is that too that's ongoing.